testing whether some independent variable x contributes to the prediction of y or not is the same as testing whether the estimated coefficient at this variable is equal to 0 or not. To do that, as always, we need to formulate two hypotheses, the null and alternative. So the null hypothesis is that the parameter beta is equal to 0, and the alternative hypothesis that it is not equal to 0. After this, we can estimate the test statistic. So the t-value will be equal to the estimated value of beta minus the hypothesized value from the null hypothesis, which is 0, divided by standard error or standard deviation of beta k. After this, we need to decide which test we have. So the one that we see here is a two-tailed test, and for this test, the null hypothesis is rejected when the estimated t-value in the absolute terms is higher than the critical t-value at the level of significance alpha over 2. When we have a negative tail test, the null hypothesis is rejected when the estimated t-value is lower than the critical value of t at the level of significance alpha. And as for the positive tail test, the null hypothesis is rejected when the t-value is higher than the critical t-value at the level of significance alpha. Alternatively, we can also estimate the p-value and compare it with the level of significance 1, 5, or 10%, and if the estimated p-value is lower than any of the significance levels, we say that the null hypothesis should be rejected. We can also construct confidence interval for any slope coefficient, and it will be equal to the following. So the lower boundary is the estimated value of beta k minus the critical t-value at the significance level of alpha over 2 and degrees of freedom n minus k minus 1, where n is the number of observations, k is the number of slopes, and 1 is just 1, multiplied by standard error, a standard deviation of beta k. So, and as for the upper boundary, it is constructed in a similar way. It's just instead of having a minus, we will have a plus. So let's go back to our example of antique clocks. Let's assume we are asked to conduct a test at 5% level of significance to determine whether the auction price is linearly related to the number of bidders. And let's note that the standard error or the standard deviation of beta 2 is equal to 8.73. So the null hypothesis is that beta 2 is equal to 0, and the alternative hypothesis is that beta 2 is not equal to 0. We are asked to use 5% significance level. First, we need to calculate degrees of freedom. So n, we know there are 32 clocks, so 32 observations. We have two slopes, beta 1 and beta 2, minus 2 and minus 1. So we get the degrees of freedom are 29, and this is a two-tailed test, so 5% needs to be divided by 2. So instead of using 5%, we will use 2.5%. And if we go to the table, we will see that the critical t-value for 2.5% and 29 degrees of freedom is equal to 2.045. After this, we need to estimate the t-statistic. So instead of beta 2, we substitute 85.95. Instead of standard deviation, we substitute 8.73, and we get the t-value of 9.85. As we can clearly see, the estimated t-value is definitely higher than the critical value, so we reject the null hypothesis. And the conclusion could be the following. At 5% level of significance, there is sufficient evidence to conclude that the number of bidders contributes information for the prediction of the auction price of a clock. So we can say that there is a statistically significant relationship between the dependent variable, which is auction price, and the independent variable, which is the number of bidders.